Okay, so we need to talk about the things that affect pressure or blood pressure. And one of the things that does affect blood pressure is the actual cardiac muscle contraction. So cardiac muscle contraction. So we're talking about contraction force here. So we know that cardiac muscle has the basic same structures as skeletal muscle with the myofibrils and all of those things. But the contraction of this cardiac muscle is a little bit different. So if we know we have a cell, the autorhythmic cell, and that is what generates the action potential to a contractile cell. So if we have the contractile cell is attached to the autorhythmic cell through the intercalated disc, and within the intercalated disc, we have little gap junctions, and that action potential, when it comes through those gap junctions into the contractile cell. So this is the action potential. So we know that it's the autorhythmic cell that creates it. It's not the brain, it's not the nervous system or anything like that. It is the autorhythmic cell, the pacemaker cell that starts it all. So that action potential comes into the contractile cell, and what happens to it? Well, the contractile cell, again, has the same structures as a skeletal muscle cell. We know that it looks different and that it's, branched and that kind of thing, but it does have T-tubules, and the action potential will run down the T-tubule. We know that the T-tubule is a structure that is really part of the membrane, the plasma membrane. Okay, so it goes down and into the T-tubule. So if you think about the skeletal muscle, you can kind of know that once it goes into the T-tubules, it opens these little doors and signals the sarcoplasmic reticulum to open. So we have sarcoplasmic reticulum here, which has, of course, calcium in it. So what's different here is that the sarcoplasmic reticulum is actually signaled to open by calcium. And calcium in a cardiac muscle also will come into that cardiac muscle cell from the extracellular fluid. So we have calcium in here, but there's also calcium in the extracellular fluid, and it will also come in the T-tubule. And there are special channels there that allow calcium into the intracellular fluid from the extracellular fluid. The calcium signals these channels to open, and then calcium will come from the sarcoplasmic reticulum into the intracellular fluid, and then the same thing happens. We get an action, or we get a muscle contraction, the same as with a skeletal muscle. So again, we have that action potential coming in, and again, we've got, these muscle cells can branch and all of that, which of course the skeletal muscle cells cannot do that. But again, we have our intercalated disc here, and the action potential then moves on and goes to the next cell, and so on. So the interesting thing about this is that because the calcium can come from the extracellular fluid, the sympathetic nervous system can actually, through the use of epinephrine and norepinephrine, can create more channels within the T-tubules of the contractile cells that can allow even more calcium into the cell. So just to write this down exactly what's happening here, we have an action potential. An action potential is generated by the autorhythmic cell, and it travels to the contractile cell. So we see that here. It's going into the contractile cell. All right, the action potential then goes down the T-tubules of the contractile cell. So we have the action potential coming to the contractile cell, and then we have it going down into the T-tubule. So AP travels down T-tubule. All right, once it gets into the T-tubule, then it will open voltage-gated calcium channels. Opens voltage-gated calcium channels in those T-tubules. So calcium then coming in from the extracellular fluid, calcium from extracellular fluid comes in through the T-tubule. All right, so then over here, 2, so 3, 4 here. Then we have calcium coming into the intracellular fluid, causing calcium channels on the sarcoplasmic reticulum to open. So this calcium then opens voltage channels on the SR. And then from there, just the same thing occurs for a contraction. You've got the calcium binding to troponin, moving the tropomyosin, exposing myosin binding sites, and then the filaments come together, the myosin comes up, goes onto the actin, and then you have the power stroke. So that's the same. That is the same as in skeletal muscle. This up here is different because we're getting more calcium. So if you look at, if we're looking at skeletal muscle, as compared to cardiac muscle here, So think of it this way. When you have a skeletal muscle and you stimulate the skeletal muscle to create a twitch, that twitch is always the same. Okay? So to get it more forceful, you would have to be able to stimulate it over and over faster before it can relax. So the twitch is the same. And each muscle fiber, or really each motor unit, is going to contract the same. So that means summation is required to increase force. So remember, we can get tetanus. And that's totally possible. That's normal, okay? In a cardiac muscle, we know that that is not normal. We don't want tetanus. We can't have tetanus, or the heart will not move blood around. So in cardiac muscle, the size of the contraction can be changed just by changing the amount of calcium. Amount of calcium that comes in from the extracellular fluid. And that's going to be a sympathetic function. So epinephrine will create more calcium channels on the T-tubule. And when more calcium comes in, so increased calcium will provide increased contraction force and increased pressure. So less calcium in there will be less force and less pressure. So that is one way that the body, or that the ANS, the sympathetic nervous system, can enhance or increase pressure, and increase force, increasing cardiac output, increasing all of those things. Okay? All right, so let's look at something else. Let's look at stretch.